same to proton donors, but a base rather than donated hydrogen is a proton acceptor. So if we take a look at water, this is called the disproportionation of water. It's where water reacts with itself. You can see that the K is really small, 1 × 10⁻14. So what does that tell you about the extent of the reaction towards products? It doesn't really happen very much, right? Mm-hmm. Do you guys see that? Smaller the number, products over reactants, right? The products are much, much, much smaller than the reactants, right? Which is to be expected. If you get a glass of water, you expect it to mostly be water, right? That's kind of what you expect. And if we write K, products over reactants, just like we would for anything. If you remember, I did tell you that everything we're going to do is the same equilibrium. We're just applying it in different situations. Which means that, well, compare the H3O plus and the OH minus in this reaction. The values. How would you compare the values? How would the number of those and the number of those compare?
1 to 1, right?
No? Want to give it a shot? How do the number of these and the number of those compare? Yeah, they got to be the same.
Yeah.
Right?
Okay.
Because, you know, 2 waters give you 1 H3O plus and 1 OH minus. So whatever the number is for H3O plus, same number has got to be for OH minus, right?
Yeah.
So in other words, right? H3O plus has to equal the OH minus. Those two together equal 1 × 10⁻14. When you take the square root of something, you divide by that number, right? So 14 divided by 2 is 7. So those numbers are all going to be like that. We talked about it a little bit, but I'll just go over it again. When people don't deal with, the general public doesn't deal well with scientific notation of really small numbers, that's just not something that you experience much in your daily life, driving a truck or whatever you're doing. And so the idea was to make it a lot easier. And so the one and only time that common logs are used in science was right here. And so rather than deal with it this way, let's just take the common log of 1 × 10⁻14, which would be -14. But then we run into another problem in that if you just hit people in the aisle at the grocery store and you say, which is bigger, -7 or -5, over half the people are going to tell you -7 is bigger, because they don't deal with negative signs very well either, okay? Which, I don't know if we have any advertising majors in here, but these are lessons that you should take to heart when you're designing your next ad campaign, okay? Because you take advantage of those facts. But witness the fact that you go to the furniture store and that couch is $999.99 because, well, it's less than $1,000. Okay, technically, yes, it's less than $1,000, but we perceive the numbers differently when we add another digit, you know? So a 99-cent Coke is a cheap Coke. $1.05 Coke, oh, that's more expensive. Not really, but okay. So anyway, so we came up with this, the letter P, which basically means the negative common log. Okay. That's what that means. So we put a P in front of something. So this is the equilibrium constant for water, so that's Kw. So pKw is equal to 14, right? Negative common log of 1 times 10 to the minus 14. This is the H3O plus, so the pH, because we still use the classical definition over here when we're doing the P thing. The pH would be 7. The pOH would also be 7, right? Negative log of 1 times 10 to the minus 7 is 1 times 10 to the minus 7, okay? Don't use pOH nearly as much as we use pH. However, if any of you have a pool, they do use the P when they're talking about things like chloride ion concentration. They'll actually, you buy the chloride strips and stuff like that, and it'll be a common log scale, 1 through 7 or something like that. So it's not uncommon to see it in other things, but basically these are the most common uses for it. But just remember, if you put P in front of something, it means negative log of it. That's just what you need to know, okay? So P pepperonis would be the negative log of the pepperonis on a pizza. That would be what it would be, okay? So, well, if I have A times B, if I take the log of A times B, log AB is what? What's the log identity for log AB? Isn't that log A plus log B? Right? Well, looky here. So pKw equals, because they're multiplied together. Okay? Okay. Well, that can be really handy. So the first thing that I think we mentioned on Friday was that this is the reason why the pH of water is 7. pH of water is 7 because the hydrogen ion concentration in water is 1 times 10 to the minus 7. And when you take the negative log of it, you get 7. It's also why the pH scale goes from 0 to 14, because pKw of water, or the pKa of water, whatever you want to call it, pKw, is 14. And so that's why that's considered the top end. The reality is that in non-aqueous systems, you can go way outside of that 0 to 14. You can imagine I could have a situation in some organic molecule where I have 10 to the minus 42nd hydrogen ions in there. Great, then I got a pH of 42. It doesn't mean anything to me because I'm not an organic chemist, but it doesn't, you can't do that in water because you're limited to the 14 over there. That's about as far as you can go. What would a pH of 0, how much acid would you have if you had a pH of 0? What's the negative log of 0 equals negative log of X? What's X?
1.
It'd be 1, right?
Yeah.
So a pH of 0 means you have 1 molar acid. Doesn't mean you have I take that back. It means you have 1 molar hydronium ion. That could be a much higher molarity of the actual acid because it may not all break up. Okay. Notice something else that comes out of this. What's the difference between pH 7 and pH 6? The difference between pH 7 and pH 6. What has happened to the hydrogen ion?
It's changed by an order of magnitude,
Yeah.
and it's gone down by an order of magnitude.
10 times.
Yeah, it's 10 times higher. Every time you change a pH unit, the hydrogen ion concentration either went up or down by a factor of 10. Those are pretty huge changes. to put it in perspective, a pH 1 solution of hydrochloric acid, you stick your finger in it, it's gonna hurt. You're gonna hurt your hand, okay? A pH 2 solution is lemon juice. That's a lot different, you know? You're talking about a tenfold difference in the amount of stuff. Okay. So you have a solution that has a pH of 8.6. What's the POH? You got a solution that's got a pH of 8.6. What's the POH?
5.4.
Yeah. 14 equals 8.6 plus X, right? So 5.4. You see how to do that? What if I have a pH of 14?
0.
My POH would be 0 at that point, right? So what does a pH, so a pH of 14 means that I have a very, very, very small hydrogen ion concentration, right? And there is a fairly large school of thought that says that we should probably just not even think about OH at all. That bases are when you have a really low hydrogen ion concentration, and acids are when you have a really high one, and not to even put OH in there, not even think about OH at all. We're going to do that because Arrhenius says OH, so we're going to keep talking about it. But I'd say there's a fairly large segment of the chemical community that just says, yeah, don't even think about OH, just think about the H. All right. So, where was I going to go with that? There was something I was going to do here, but I've now forgotten what I was going to do. What's the conjugate base in the reaction I've written up there? Conjugate base in the reaction I've written. What's conjugate base?
OH minus.
Well, what's base?
H2.
According to Ross and Lowry, what's base?
Protonic separator.
Protonic separator. Okay, who in the products is going to accept a hydrogen to look like the reactants?
H2O.
The OH, right?
Yeah.
Yeah.
And so the OH, because it goes from OH to H2O, right? So it's going to gain a hydrogen. So it's the base. If it's a product, it's a conjugate. All right, remember that?
Yeah.
So anytime I say acid base, acid means it donated lost a hydrogen. Base means it gains a hydrogen. Conjugate means it's in the products. Okay, that's just all it means. Let's get that terminology down so you know what I'm talking about. So this is your conjugate base. So this would be your conjugate acid. Well, one of these is the acid, one of these is the base. I can't tell them apart, so I don't know which one's which, right? But one of them is. And according to Bronsted-Lowry, actually, all these reactions, all the reactions that happen out there are acid-base reactions. They're all, somebody gets a proton, somebody loses a proton. That's what's going to happen. That's what's happening to all these reactions. Okay, so let's talk just generic acid here. So acids, by convention, acids always start with an H. Okay? For example, acetic acid. Acetic acid actually looks like this. Okay, that's acetic acid. It's got 4 hydrogens on it. So how do we know how many hydrogens it's going to give off? And the way we know is by convention, we write the acidic hydrogens first. So this becomes HC2H3O2. And now I know that that hydrogen is acidic and the other ones are not. Okay? Citric acid, H3C6H7O3. Maybe O6, I don't know. Okay, so this one has 3 hydrogens that are acidic, 7 hydrogens that are not acidic. Okay? So anytime you see an acid, it's going to start with an H. Okay? And you will know how many acidic hydrogens it has because I will list those, or whoever it is, whatever textbook or whatever is going to list it. Okay? So it's always going to be H2SO4, or HCl, or HC2H3O2, or H2C2O4. Doesn't matter. Whatever it is, it's always going to have the acidic hydrogens first. And then if you get down in there, you can say, well, which one of these is it? If you care about that, you can figure that out. Although it's going to be this one. I know that, but whatever. But typically not relevant for what we're doing in general chemistry. When you guys get to organic, a lot of you are going to take organic, it becomes hugely important. But right now, you don't need to worry about it. Okay. So let's talk about just a generic acid. HA, let's say. Because one of the things you're going to notice pretty soon is that when you're talking about acids and bases, the identity of A, not very important. All you need to know the A for is so that you can figure out what the equilibrium constant is. But if I tell you have HA and it has equilibrium constant of 1 times 10 to the minus 5th, you got everything you need. You don't need to know what A is. Okay? So we just have some, this is one of those where chemists actually count higher than normal. Remember, usually it's 1 lots. This one is 1, 2 lots. Okay, that's pretty good for us. I count up to 2. Okay, so this would be how many acidic hydrogens do I have on here? 1. So this is a monoprotic acid. 1 proton. And if I have 2 hydrogens, a diprotic acid. And if I have 3 hydrogens, now you'd think so,
Poly.
but it's poly. We only go 1, 2 lots, okay? At that point, we say it's a polyprotic acid. The really lazy chemists will even say diprotic is polyprotic.
Oh, okay.
They're in the minority. They're the super lazy ones. Okay, so we have a monoprotic acid here. We're going to react it with H2O. Think about Bronsted-Lowry and all that kind of stuff. Take a second, write the products. What products would you expect to have? And then tell me the acid, the base, the conjugate acid, the conjugate base. Products, acid, base, conjugate acid, conjugate base. Which one's going to give it birth? Well, don't you know it's a monoprotic acid? It's got to be like that. So what's left? But now A's got a charge. It just lost plus H plus. And then who's the base? Okay, now I just told you that HA was a monoprotic acid. And a Bronsted-Lowry acid does what? What does an acid do?
Gives us
Donates.
Donates a hydrogen, or it gives it up, right? A hydrogen's gonna go away. It's gonna lose a hydrogen. So that means all I have left is A, because I just lost my hydrogen. But hydrogen's got a +1, so A's got what charge?
Negative, -1.
Okay, well, if that's the acid, then that's gotta be the base. And what does the base do?
Receives information.
It accepts a hydrogen. Oh, so what's it gonna be? H3O, because I just gained a hydrogen,
Plus.
and it's gonna have a plus charge because it gained an H+. Right? Okay. So what's my conjugate acid and conjugate base? Who's going to lose a hydrogen going that way?
H3O.
H3O, right?
So that's the conjugate.
So this is my conjugate acid. This is going to gain a hydrogen, so that's my conjugate base. Now, you may have figured this out already, but here's just an FYI. If you ever are tempted to say H3O plus is a base or OH is an acid, you're doing it wrong, okay? Because those are pretty much the Arrhenius definitions of acid and bases, right? So you can't, no. So when you see H3O and something, you're like, cool, that's the acid. I know it's an acid. It may be a conjugate, may not be, depending on which side of the reaction it's on, but it's definitely an acid. All right. Can you, let's put a AQ right there. Can you write the equilibrium constant for this reaction? Equilibrium expression, sorry. Can you write the equilibrium expression? Remember, products over reactants, raise the power of the coefficients, ignoring liquids and solids, right?
Yeah.
Do we have any liquids or solids in there?
Yeah.
What? Water.
Water.
So we ignore the water. Okay, cool.
I look at the water.
So that means my K is A minus over H3O times H3O plus over HA. And we ignore the water, right? Okay. Now, this is the equilibrium constant for an acid. So it's a Ka, K for acid. You'll never guess if it's a base, what kind of K that would be. Oh, you guys figured it out. Okay, yeah, right. Okay. So if it was a base, it would be a Kb. Okay. So there is our, so that's the general form of any acid. So let's do this. You have 0.1 molar stuff. And you're told the Ka of this is 3 times 10 to the minus 8.
Well, let's work it out.
What's the pH? We're going to follow the normal rules for equilibrium. Normal rules for equilibrium. Which is what? Set up our ice table, probably? Something like that.
Yeah. If you insist.
So before I start breaking any HA up, how much H and A do I have?
Well, at 0.
Before I start breaking anything up, how much broken up stuff do I have?
0.
None, right? Because I haven't started breaking it up yet,
Yeah.
right?
Yeah.
Okay. Okay. How much of this is going to break up? Do I know how much is going to break up? No,
No.
I don't know. And when I don't know,
We find out.
Minus
x, sure. So x of it's going to break up, so it'd be minus x, right? And if x of this breaks up, how much of this is going to form?
X.
X, because they're the 1 to 1, right? How much of this is going to form?
X. And there's so many lines picture.
Oh, looky here.
Wow.
So that's equal to 3 times 10 to the minus 8, which is equal to x times x over 0.1 minus x. That looks solvable. Shall we try to make our lives a little easier? Let's try to drop this out. If x is really small relative to 0.1, then we can drop that x and not have to deal with quadratic. Okay? Those of you who got TI 84, 85, 86, 89, 94, 118, whatever we're up to these days, then you can just plug in the numbers and it automatically does a quadratic. You can always ignore this and just do the quadratic. For the rest of us, I don't want to do the quadratic. So, what do we have here? 3 times 10 to the minus 9th equals x squared. Square root of 30, that's like 5.5 or something. So like 5.5 times 10 to the minus 5th, something like that.
Why is
Yeah.
it, why is it x to the 7?
What?
Why is it x to the 7?
That's this.
You're
Oh, x
below.
times x is x squared.
No, below it. 0
You're-
below minus x to the 7.
This?
Multiplying.
This?
That, yeah.
Oh no, that's an arrow.
Ah,
That was. How about that? Is that better? Yeah. Five, 6, 5, 5,
5.5, yeah.
It's 5 what?
5 times 10 to the power negative
It's just 5?
5.47.
5.5, yeah.
Minus 5th, right? Okay. Huh. But that's equal to the H3O plus. It's also equal to OH, but we don't care. Okay? So that's equal to the H3O plus. Oh, sorry, not the OH. It's also equal to A minus. A minus. But we don't care. Okay. So what's the pH?
Plug it in.
Yeah. Is it 5? It's in the ballpark of 5, but it's not quite 5. How do we find out what the pH is? Do you remember what the pH is? What is definition of pH?
Negative log.
Negative log of the H, right?
Yeah.
And we know the H.
I get 4 times.
So we put that number in and we go negative log. Or depending on your calculator, you go negative log and then put the number in. Depends on how your calculator works. Okay.
4.3.
So the negative log of 5.5 times 10 to the minus 5th equals the pH, which is equal to, you said 4.3? Okay, 4.3. Right.
Yeah.
What's pOH? pOH. What's pOH of this solution?
14 minus 4.
What is it? What is it? What you got? 9.7? Okay, 9.7. Because pH plus pOH equals 14. If I know the pH, I know the pOH because the two added together have to equal 14. Right? You see that? pH plus pOH equals 14.
I just didn't know it was still 14.
Yeah. Okay. This makes a huge difference. So for example, let's say this was yogurt. When you get to 4.3, the yogurt gels up. If you're at 4.7, it's still liquid. The difference in that 0.4 pH units is the difference between gelled up yogurt and a little runny milk, sour milk. That's the difference there, okay? As the pH goes down, what taste does acid have? Anybody know? Acidic foods tend to be what? What?
Sour.
Sour. And so the lower the pH gets, the more sour they are. Lemon juice has a pH of 2, it's very sour. Orange juice has a pH of like 3.5, it's much less sour, right? By the time you get to like a peach or something, it's probably got a pH of about 6 or something like that. So, yeah. So, not sure how much it has to do with anything, but I'm a food chemist, so I got to mention it. Americans don't really like sour foods. We are much more into sweet. Any of you who are not originally from America know that everything you eat here is sweet. As a matter of fact, one of the biggest complaints I hear from people who come from overseas is, oh my gosh, even your bread is sweet. What the heck? All your loaves of bread are sweet. We don't notice it because we've always had sweet bread. But Americans don't like sweet. So how do you get them to eat yogurt? Because yogurt's sour.
Put sugar in it.
You put so much sugar in it that you can't taste the sour anymore, right?
Oh.
So what you have to do, what they do at the yogurt manufacturer is if you take a look at yogurt, like the stuff that's in the little cans, not the, because plain yogurt only comes in large containers because you actually have to like yogurt to buy it that way, right? And it's down at the bottom where nobody can find it, right? But the sweet stuff is right there at eye level for your typical tween. Okay, so anyway, so you take a look at those yogurts, here's what you'll notice. They all have pectin in them. Because the way you keep it from being sour is don't lower the pH. Don't lower the pH all the way to 4.3. Stop it at 5. Well, now it's not gelled up. So what do? You add pectin, like from jelly, making preserves or something. You add pectin to it, and that makes it gel up. And then you add a whole bunch of sugar. And now suddenly you have not sour stuff. As a matter of fact, a serving of American flavored yogurt has more sugar in it than a serving of Lucky Charms marshmallow cereal. That's how we made it attractive to Americans, is by putting more sugar in it than marshmallow cereal does. Okay. All right. So, all right. Oh, let's try it. Let's do this. Let's keep the same one. I want a pH of 3.9. What concentration of acid do I need to put in there? It's the same acids we were just doing over here. It's the same one, same Ka. I want it to be 3.9. What do I know? I know the negative log of x equals 3.9, right? So I don't know what that number is. 8 or 9 times 10 to the minus 4, something like that. Somebody's going to tell me here in a second. So maybe 1.3 or 4. I can't do logs in my head. It's what?
1.2.
1.25 times 10 to the minus 4th, is that right? Okay. I know the final equilibrium H3O concentration because I know it's 3.9, right? And if the H3O concentration is 1.25 times 10 to the minus 4th, what's the A minus concentration have to be? Look at the reaction up there. It's got to be the same thing, right?
Yeah.
Because 1 HA turns into 1 A minus plus 1 H3O plus. So if I know one of them, I know the other one. Do you see that?
Yes.
So now my algebra is going to be a little different. So now I start at 0 here, but I know this is 1.25 times 10 to the minus 4th, and I know this is 1.25 times 10 to the minus 4th. Because I know its pH is 3.9. I know that. So that means this must be 1.25 times 10 to the minus 4th also. Which means this is minus 1.25 times 10 to the minus 4th. So what am I missing? I'm missing this.
X.
Can you solve that?
Yeah.
Should be able to.
Already. Just do this.
We got a number?
Yes. 0.53.
0.53?
Yeah.
Now, for those of you that want to do a little less algebra, there's no reason why we can't make the same assumption we made before, even though I know what the number is, right? I could say, if 1.25 times 10 to the minus 4th is much less than x, then I can cross out that term. Which means that x equals 1.25 times 10 to the minus 4th squared, that's a squared, over 3 times 10 to the minus 8. Which you told me is 0.5?
Yeah. Give or take.
Is 0.53 small, is 0.53 much, much larger than 1.25 times 10 to the minus 4th? Sure, so it was a valid assumption. And anybody who did it the long way, if you did it the long way, you're still gonna get 0.53.
Yeah.
The difference is gonna be in like the 5th or 6th decimal place where it's beyond our error anyway. So, okay. So now you can see, and this is commonly done, right? How much acid do I need to put into my pool before I get a pH that allows me to go swimming in the pool?
That much.
You know, well, I probably don't want to swim in a pool that's got a pH of 3.9, but whatever.
Yeah.
Good. Good. You know. So don't really see it done this way very much as far as like home pool manufacturers and stuff like that. But however, this is a very common way of doing, like, how much fluoride do I need to put in the drinking water, I have to calculate that number, and I have to know, okay, I have to put this much in, exactly this many grams of stuff, because otherwise all of your teeth are going to turn brown and have spots all over them because you're going to get fluoridosis. So, that's a huge thing. And so, there are times when you really have to know how much stuff you're putting in there. All right. Okay, let's see, what else can we do with this? Oh, let's talk about this other thing too. Remember, that? So on Friday, we talked about this a little bit. So I'm reviewing this again for you guys. On strong versus weak, talks about how much of it breaks up. A strong acid, all of it breaks up. It all goes from HA to H plus and A minus. Okay? A weak acid is some number less than 100%. Typically a lot less than 100%. So, you have 0.1 molar solution of vinegar. What percentage of it breaks up? So first off, vinegar, strong acid, weak acid. Weak acid, how do I know it's a weak acid? Because Ka has a value.
Yeah.
Strong acids completely break up. Products over reactants, if reactants are 0, goes to undefined, which we know from pre-calc takes us to the limit equals infinity, right? So 1 over x, as x goes to 0, is infinity, the limit, right? And so if you have a value for pKa, means you have a value for Ka, which means it's a weak acid. Strong acids just have very large, infinite, something like that, depending on what book you look at. Okay? So, we got a weak acid, which means less than 100% is going to break up. How much of it breaks up? So what are we going to do first?
Ice.
Set up one of those tables, just like we did before. You got a 0.1 molar solution. Okay? Hold it, what's the formula for acetic acid? Don't care. It's got an H. That's all we care. It's H, acetic acid. What's acetic acid? Something. Okay? It doesn't matter.
X over X squared.
Here we go. It's acetic acid. There. Okay. Now we changed it. Okay. So now it's acetic acid because it's got a C in there. Acetic acid. Okay. Okay. There we go. So I know it starts at 0.1. Minus x, x, x. What is a pKa of 4.74? How do I turn that into a number? What does P stand for?
Negative log.
What does P stand for? Negative log. So the negative log of the H plus is 4.74. Can you solve for H plus?
Yeah.
4.74 equals minus log base 10 of the H3O plus. That's what pH means, right? Which means, get rid of the negative sign over there. How do you get rid of a log? Raise it to the power of its base, right? So 10 to the both sides cancels that. So the H3O plus is equal to 10 to the minus 4.74. And assuming you don't have the little 9-button calculator you got free with a subscription to Sports Illustrated, you have a calculator that can do that. So. Although you may have to turn your phone sideways to turn it scientific. Oh, that's not even, whoops. Sorry about that. That was pKa, not H plus. So, sorry, my mistake. So the Ka is that. So let's see what we have. So 10 to the minus 4.74 equals x squared over 0.1 minus x. We're once again going to try to get rid of the x. So 10 to the minus 5.74 equals x squared. What's that number? It's a number. This is 10 to the minus 1. When I pull that over here, I have 10 to the minus 4.74 times 10 to the minus 1, which adds exponents. Minus 4.74 plus minus 1 is 5.74. If you prefer, turn that into a number, then multiply by 0.1. Works the same way. What do we get for x?
0.0013.
0.0013. 1.3 times the minus third?
Yeah.
Okay. What percentage of the acetic acid breaks up? How do you do percents? Percent. Not in chemistry, just in math. How do you do percent? Any percent. What percent of your body weight is your head? How do you figure that out? You take your part, the head, divided by the whole weight, right? So it's part divided by the whole times 100. Okay, the part is what broke up. What's the part? Okay, what's the whole?
0.1.
0.1 times 100, and you get 1.3%.
Yeah, 1.3%.
So notice in this vinegar, so 1.3 times 10 to the minus third divided by 0.1 times 100. So only 1.3% of the acetic acid broke up. Not very much of it. 98.7% did not break up. So you can see the difference between a weak acid and a strong acid. If we had a strong acid here, this is what, about 2.9 or something like that? I don't know, what's this number? 3.1? What is the negative log of that number?
Oh,
Like 3.1 maybe? Is that right? 3.2?
2.9.
2.9, okay. This is like 2.9. What if it was a strong acid? What if it was a strong acid? If it was a strong acid, what would this X be right here?
0.1.
It would be 0.1 because it would all break up,
Yeah.
right? This value here would be 0. So this number right here would be 0.1. And the negative log of 0.1 would be 1.
Yeah.
So the difference between it being a weak acid and a strong acid is the difference between having a pH 2.9 and a pH of 1. Would you think, well, that's not that big, that's only 2 pH units. But remember, that's 100-fold difference in the amount of hydrogen. Because every time the pH goes down, the hydrogen goes up by a factor 10, right? So that's a huge difference there. Okay, cool. See you Wednesday, guys.
Actually, she asked us to go.
Yeah.